So if you look at this case, yeah, ma? Yeah, if you look at this case also, it's exactly same as that you have, okay, as Sanjana has just explained. Okay, now electric force is also an inverse square law force, except in place of capital G we have 1 by 4 pi epsilon naught. Okay, and in place of M1 M2 you have Q1 Q2. R square is same again. Okay, so the electric field force is Q1 Q2 by 4 pi epsilon naught, and r square is the distance between the two charges, and r square is the distance between the two charges. If you have charge, okay, in this region, okay, where my cursor is running, if you have charge in this region, this charge does not have any net effect on the charge that is present at this place, that is plus symbol. Why, sir? Okay, does this charge does not act? Yeah, it does act. Okay, all the charges that are above are closer to this charge, and all the charges which are far, okay, is more. Okay, this charge is more but far, but this charge is less but nearer. So what happens is the net pull by this charge is compensated by the net pull by this charge in opposite directions, because of which this charge plus charge does not experience any charge which is in this annular region. Okay, so if you want to find out what is the net force between these two separated charges, that is negative charge and positive charge, then you have to find out what is, okay, Q1 Q2 by 4 pi epsilon naught r square. Okay, when I'm talking about okay, two separated charges. Okay, just two charges. Okay, clear? Q1 Q2 by 4 pi epsilon naught r square. Okay, where r is the distance between the two charges. Okay, good. If it is two charges, the point is, if it is a continuous distribution. Okay, in a sphere, if you have charge in a dielectric sphere, you know that the resultant charge can be supposed to be at the center. You can consider that the resultant charge is at the center. Okay, right? So now with this explanation, I go to this place. With this explanation, I go to this place. Okay. Okay. Now this is an atom. You have positive charge and negative charge at the same point in an atom. Okay, it's a spherema. Okay, and I don't have any field. I did not apply any field. Okay, so the total charge over here is Ze, okay, of the negative charges, and Ze for the, okay, charges in the nucleus. Okay, Z is the atomic number, E is the unit of charge. Okay, so we have Ze amount of charge, negative charge in the outside, and Ze amount of charge inside the nucleus. Okay, good. Now, if R is the radius of the atom, then the volume of this atom is 4 by 3 pi r cube, because atom is a sphere. Okay, so this complete negative charge is distributed in this complete sphere. So the charge density of this negative charge is Ze by 4 by 3 pi r square. Ze by 4 by 3 pi r square. Okay, now if I consider this as a negative charge, then you'll have a okay, minus sign over here. So for the time, okay, for the time being, forget about the negative sign. Okay, so Ze amount of charge, that is electrons, are distributed in 4 by 3 pi r square, pi r cube volume. So charge density is Ze by 4 by 3 pi r cube. Okay, now this is a neutral atom. Why is this neutral? Because positive charge center and negative charge center are at the same point. So this is a neutral atom. On this neutral atom, an electric field E is applied. When I apply an electric field E on this neutral atom, so I'm applying an electric field here. When electric field is applied, okay, here. So I have applied an electric field in this direction. Okay, this arrow gives me the direction of the applied electric field. When you have applied this electric field, what happens to the positive charge and what happens to the negative charge? This is what happens. Okay, so when there is no applied electric field, positive charge center and negative charge center will be at the same point. So the net dipole moment of this atom is 0. But when you apply electric field in this particular direction, then okay, you say that the positive charges are here and negative charges this side. So the negative charges will be deflected to the left and positive charge will be deflected in the direction of the applied field. So because of which there is a charge separation now, charge separation. Because of this charge separation, there will be dipole moment. Okay, good. Because of this charge separation, will there be a net attraction? Yes. Which one? So now, okay, your part, okay, this is the charge separation between the positive charge and negative charge. Let me say it is X. Let me say the charge separation between positive charge and negative charge is X. Okay, because of this X separation, okay, whatever charges you have, okay, in this particular region, okay, in this particular, okay, I'm sorry, okay, figure wrong draw చేశాను. Okay, ఇక్కడ ఇటువైపు ఉండాలి. Okay, I don't know whether you understood part or not. Okay, let me see. Okay, is that clear now? Yama, did you understand?
Yes, sir.
Okay, once again, this is the neutral atom. I have applied electric field in this direction, because of which negative charge centers will move to the right side and positive charge center will move to the left side. Okay, so this is how you got a charge separation. Okay, let me say that this charge separation is X. So that implies now this figure is being recreated. This right side figure is being recreated. Right side figure got recreated now. Okay, now what is this? Now this is the separation between the positive charge and the negative charge. Okay, so what will be the net force of attraction? Okay, the net force of attraction depends upon the charge you have here, that is Ze plus, because all the positive charges at the center of the nucleus, Ze plus, and the charge that is enclosed in this particular sphere, and the charge that is enclosed in this particular sphere, as you have said that this is the charge, okay, this is the mass that actually affects. So I need to know what is the what is the charge that is enclosed in this sphere. So to know that, nothing much. Okay, the charge enclosed in this sphere is nothing but the volume of this sphere, this volume of this internal sphere into the charge density, So this volume of the sphere is 4 by 3 pi x cube, and charge density as you have calculated is Ze by 4 by 3 pi r cube. Okay, so charge density. So this is the charge that is enclosed in this particular internal surface. Okay, now if at all if you forget about charges, it is exactly same as you have taken an object from the surface of the earth to below the surface of the earth, because of which only the surface below will be responsible for the attraction. Exactly in the same way, okay, only the charges which are below this positive charge, are responsible. Sir, how to know how many charges are there? Nothing. I have already calculated the volume, okay, volume density of the charges. So find out this volume and multiply with the volume density. I'll get the total charge inside this sphere. Okay, so the total charge inside this sphere is Q dash. Okay, so that expression is okay, 4 by 3 pi x cube rho. So that implies this one, or to say Q dash is equal to x cube Ze by r cube, x cube Ze by r cube. I just cancelled the, okay, 4 by 3 pi. Okay, so x cube Ze by r cube, nothing, right? So that is the charge enclosed in this sphere. Okay, very good, sir. You calculated the charge enclosed in this sphere. Okay, at this instant, there will be two forces acting. One, Lorentz force due to the applied field. Now this applied electric field has actually created this separation, right? So E into Ze, okay, will be the force acting on negative charges as well as the positive charges. Okay, now when these two charges got separated, Coulomb force comes into picture. Okay, Coulomb force comes into picture. Now what is the Coulomb force? Q1 Q2 by 4 pi epsilon naught r square. Q1 Q2 by 4 pi epsilon naught r square. What is Q1? Okay, positive charge that is inside the nucleus, that is Ze, and negative charge. What negative charge? I have to take the negative charge which is enclosed in this sphere. Okay, so the amount of negative charge that is enclosed in this sphere is q dash. Okay, Ze plus into q dash minus by 4 pi epsilon r square or x square, because x is the separation between these two. Okay, now this is the Coulomb force. Clear? So in this particular situation, after applying the electric field, okay, here you don't have any new, okay, net, okay, force. But after applying the electric field, okay, we have two forces. One is Lorentz force because of the electric field, that is Ze into E. And another is Coulomb force, that is Q1, Q2 by 4 pi epsilon r square. Okay, here Q2 is nothing but Q dash and R is nothing but your X. This way I have two forces. Okay. Now, will the separation go on? Will the separation go on? No, no. Okay, they stop. When do they stop? When they reach equilibrium. Okay, when do they stop? When they reach equilibrium. So when they reach equilibrium, okay, Lorentz force is equal to the Coulomb force. Lorentz force is equal to the Coulomb force. That implies